Hello there, and welcome to Mysteries Beneath Earth. Tonight, we are going to look down, not just at the floor beneath your feet or the foundation of the building you rest in, but much, much deeper. We are going to cast our minds into the dark, crushing, incredibly hot expanse that lies just a few miles below where you sit right now. We often move through our lives with a profound sense of stability. The ground feels solid. The mountains look eternal. We build our cities of stone and steel, anchoring them to the crust as if it were a permanent stage for our history. But if you were to look at the Earth not as a human sees it, but as a geologist or a physicist sees it, that sense of solidity would vanish instantly. The truth is, we are living on a raft. A very thin, fragile raft of cold rock floating on a deep, churning ocean of heat. If you were to shrink the Earth to the size of an apple, the crust, the only part of the planet we have ever touched, the only part where life as we know it exists, would be thinner than the skin of that apple. Beneath that delicate skin lies an engine of unimaginable power, a furnace that has been burning for 4.5 billion years. Tonight, we are going to ask a question that bridges the gap between geology and imagination. What if that core, that furnace, is not just a relic of the past, but the ultimate future of energy? What if the power to run civilizations for eons isn't found in the wind or the sun, but in the fiery heart of our own world? To understand the scale of this energy, we have to strip away our daily experience. When we think of heat, we think of the sun. It warms our skin, it drives the weather, it grows our food. Solar energy is vast, pouring onto the surface every day. But the heat inside the Earth is a different kind of monster. It is a trapped heat, a primal heat. Scientific models estimate that the temperature at the center of the Earth is roughly the same as the surface of the Sun, about 6,000 degrees Celsius. But unlike the Sun, which radiates its energy out into the cold void of space, the Earth holds its heat close. It is insulated by thousands of kilometers of rock. It is a pressure cooker that has been simmering since the dawn of the solar system. Imagine for a moment that you could see energy as light. If you looked up, you would see the blinding glare of the sun. But if you looked down, and if the rock were transparent to this energy, you would see a glowing ember beneath you, a red, pulsing sphere of power. For most of human history, this energy has been a mystery, or a source of fear. It revealed itself only in catastrophes. A volcano erupting, spilling molten rock across the land. A geyser shooting boiling water into the air. An earthquake shifting the ground. These were reminders that the Earth is not dead. It is alive, and it is restless. But what if we stopped fearing the restlessness and started listening to it? The total heat flow from the Earth's interior to the surface is estimated by geophysicists to be about 47 terawatts. That number sounds enormous, and it is. It is roughly double the total energy consumption of all humanity combined. And that is just the leakage. That is just the heat that escapes naturally, the waste heat of the planetary engine. The actual stored thermal energy within the Earth is almost incalculable. It is a reservoir so vast that if we could tap even a tiny fraction of a percent of it, we could power our entire civilization for millions of years without ever burning another drop of oil or splitting another atom. This idea challenges us because it requires us to rethink our relationship with the planet. We have always been surface dwellers. We harvest what grows on the crust. We dig shallow holes for coal and minerals. We catch the rain and the wind. We are like creatures living on the shell of a giant egg, completely unaware of the yolk inside. But the shell is cracking. As our hunger for energy grows, and as the consequences of burning the surface become dire, our eyes are turning downward. We are beginning to realize that the ground beneath us is not just a foundation. It is a battery, a massive, planetary-scale battery that was charged billions of years ago and is still holding its charge today. However, tapping into this battery is not like putting up a solar panel. It is a journey into a hostile, alien world. The conditions inside the Earth are more extreme than anything on the surface of Mars or Venus. The pressure is crushing. The heat is enough to melt the tools we use to measure it. The rock itself becomes plastic, flowing like slow molasses. To reach this energy, we have to overcome physics itself. We have to drill deeper than we ever have, into places where the rules of engineering break down. And there is a deeper, more philosophical question here too. The Earth's heat is not infinite. It is vast, but it is finite. It is the lifeblood of the planet. It drives the tectonic plates that recycle the continents. It powers the magnetic field that shields us from cosmic radiation. If we start draining this battery, do we risk killing the engine? Is the Earth's core a resource to be used, or is it a vital organ to be protected? These are the questions we will wander through tonight. As you lie there, feeling the support of the bed or the chair, try to visualize the layers beneath you. Through the floorboards, through the concrete foundation, into the soil. Past the water pipes and the tree roots, past the layers of sandstone and granite, down, down, into the crust where the rock gets warm, then hot, then scorching. You are sitting on top of a sleeping giant. The silence of the room around you is deceptive. Below, there is the slow, grinding movement of continents. There is the convection of the mantle, a slow-motion boiling of solid rock that takes millions of years to turn over. And at the center, the iron heart, spinning, generating the invisible force field that keeps our atmosphere from being stripped away by the solar wind. We are going to explore how this heat got there. We are going to look at the violent birth of our world, a time when the Earth was not a blue marble, but a ball of molten fire. We are going to look at the silent, invisible fire of radiation that keeps the heat alive. We will travel to the frozen lands of the North, where engineers have tried to pierce the crust, and to the volcanic islands where people are already plugging their cities into the magma. And we will cast our minds into the future, to a time when humanity might no longer look to the stars for salvation, but to the depths. This is a story of fire and stone. It is a story of the oldest energy we know, and perhaps the newest. It is a story that asks us to reconsider what it means to live on Earth. Are we merely passengers on a rock? Or are we the engineers of a planetary spaceship, finally learning how to open the engine room door? Let your breath slow down. Let the worries of the day drift away like smoke. And let's begin our descent. The crust is thin, the night is long, and the mysteries beneath the Earth are waiting. To understand the energy that hums beneath our feet, we have to go back. Not just thousands of years, or even millions. we have to go back to the very beginning, to the violent, chaotic birth of the solar system 4.5 billion years ago. The heat we are talking about tonight, the heat that could potentially power our future, is a ghost. It is the lingering thermal memory of the Earth's creation. Imagine the solar system before there were planets. There was only a vast, swirling cloud of gas and dust, the solar nebula. In the center, the sun was igniting, a newborn star pulling in the lion's share of the material. But around it, in the disk of dust, chaos was brewing. Tiny grains of dust began to stick together, held by electrostatic forces. These grains became pebbles. Pebbles became boulders. Boulders became mountains. This process is called accretion, and it is a violent, energetic business. Every time a rock smashed into another rock, kinetic energy, the energy of motion, was converted into thermal energy, heat. Imagine clapping your hands together hard. You feel a sting of heat. Now, imagine that on a planetary scale. Imagine mountains of rock slamming into each other at speeds of thousands of kilometers per hour. The energy released in these impacts was cataclysmic. As the proto-Earth grew larger, its gravity increased, pulling in more debris, accelerating it to even higher speeds. It was a bombardment of cosmic proportions. The young Earth was not a solid rock. It was a molten ball, glowing red-hot in the darkness of space. This is the first source of the Earth's internal energy, primordial heat. It is the trapped heat of impact. The Earth was effectively forged in a blacksmith's fire, hammered into existence by billions of collisions. Because rock is a terrible conductor of heat. Think of how a stone stays cold on the inside even if you leave it in the sun for an hour. This heat could not escape quickly. As the outer layers of the planet eventually cooled and hardened into a crust, they formed a blanket, a thermal insulator that trapped the fire of creation inside. The heat that warms the deep mines of South Africa today, or fuels the geysers of Yellowstone, is in part the same heat that was generated when the Earth was just a baby, billions of years ago. But accretion was only the first act. As the Earth grew, something else happened, something geologists call the iron catastrophe. This sounds dramatic, and it was. In the early molten Earth, everything was mixed together. Silicon, oxygen, iron, nickel. It was a chaotic stew. But as the planet melted completely, gravity took hold of the denser materials. Iron and nickel are heavy metals. Silicon and oxygen, which make up most rocks, are lighter. Imagine a glass of water and oil mixed together. Eventually, they separate. The oil floats and the water sinks. On the molten Earth, the iron droplets, billions of tons of them, began to sink. They fell through the viscous, molten rock toward the center of the planet. This wasn't a gentle settling. It was a planetary collapse. The falling of all that iron toward the center released a tremendous amount of gravitational potential energy. Friction generated heat as the iron plunged downward, heating the planet even further. This event, the segregation of the core, likely raised the Earth's temperature by another 2,000 degrees. It was the moment the Earth got its heart. The iron gathered in the center, forming the core, while the lighter, rocky material floated up to form the mantle and the crust. So, when we talk about tapping into the Earth's core energy, we are talking about tapping into the energy of gravity itself. We are harvesting the energy of the falling iron that sank 4 billion years ago. It is a battery charged by the falling of a planet into itself. But there is a third player in this early thermal drama, the moon. We often think of the moon as a cold, dead companion, but its origin is a story of fire. The prevailing theory is that a Mars-sized object, often named Theia, slammed into the young Earth during this chaotic early period. This collision was so powerful it nearly destroyed the planet. It liquefied the crust and mantle, splashing vast amounts of material into orbit, which eventually coalesced to form the moon. The energy of this impact was absorbed by the Earth, adding yet another layer of thermal intensity to the mix. These three events, accretion, the iron catastrophe, and the giant impact, loaded the Earth with an immense thermal budget. If the Earth were a smaller body, like Mars or the Moon, this heat would have radiated away by now. Smaller objects have a large surface area compared to their volume, meaning they cool down fast. Think of a cup of coffee versus a giant soup pot. The cup goes cold in minutes. The pot stays warm for hours. The Earth is a very large pot. It has a massive volume of hot rock and metal, covered by a relatively thin, insulating lid. It simply hasn't had time to cool down. This primordial heat accounts for roughly half of the heat flowing out of the Earth today. That is a staggering realization. 50% of the energy driving the movement of continents, pushing up the Himalayas, and tearing apart the Atlantic floor is simply the planet trying to cool down from its birth. It is a cooling process that takes eons. We are living on a cooling ember, but the ember is so large that to us, creatures of a few decades, it seems eternal. When you look at a volcano, you are seeing the Earth trying to sweat. You are seeing the planet venting some of that primordial anger. The lava that flows down the side of a mountain is a liquid memory of the solar system's chaotic beginning. And this is where the concept of energy source becomes so fascinating. Usually, when we burn coal or gas, we are burning ancient sunlight trapped by plants. When we use wind, we are using current sunlight driving the atmosphere. But geothermal energy is different. It is cosmic energy. It is gravitational energy. It is the energy of the universe's construction, trapped in a sphere of rock. If we could build a technology to access the deeper layers where this primordial heat is stored, we would be connecting our civilization to the birth of the world. We would be drawing power from the collision of asteroids and the sinking of iron. It is a connection that feels almost mythological. We would no longer be dependent on the whims of the weather or the finite chemistry of fossilized swamps. We would be plugged into the planetary engine itself. But as we said, this is only half the story. If the Earth only had this primordial heat, it would have cooled down much more than it has. Calculations done in the 19th century by the famous physicist Lord Kelvin tried to estimate the age of the Earth based on how long it would take a molten ball to cool to its current temperature. Kelvin calculated that the Earth was only between 20 and 400 million years old. He was wrong, wildly wrong. He was missing a crucial piece of the puzzle. He didn't know that the Earth has its own internal fire, a way of generating new heat even as the old heat fades. He didn't know about the silent decay. There is a second furnace inside the Earth, one that doesn't rely on the violence of the past, but on the subtle quantum instability of matter itself. This is the furnace that kept Kelvin's calculations from working, and it is the furnace that keeps the Earth alive today. As we move deeper into the mystery, we must turn our attention to the invisible fires of the periodic table. Lord Kelvin's mistake was an honest one. In the 19th century, no one knew that matter could contain its own energy source. The atom was thought to be a stable, indivisible billiard ball. But as the 20th century dawned, humanity discovered radioactivity. We learned that certain heavy elements are unstable. They are unhappy with their own existence. Their nuclei are too large, too crowded with protons and neutrons, and so, spontaneously, they break apart. They decay, and when they decay, they release a tiny, invisible pulse of heat. This brings us to the second great source of Earth's internal energy: radiogenic heat. While the primordial heat is the leftover memory of the Earth's birth, radiogenic heat is the ongoing metabolism of the planet. It is happening right now, in the rock beneath your feet, in the granite of the mountains, and deep within the mantle. The Earth is, in a very real sense, a slow-burning nuclear reactor. The fuel for this reactor consists primarily of 4 isotopes. You have likely heard of uranium. Uranium-238 and uranium-235 are heavy, unstable elements that were forged in the explosions of dying stars, supernovae, long before our solar system existed. When the Earth formed, it swept up these heavy elements from the cosmic dust. Then there is thorium-232, another heavy radioactive metal. And finally, potassium-40, a radioactive version of the common element found in bananas and your own body. These elements are not found in high concentrations like they are in a nuclear power plant fuel rod. They are scattered. They are trace elements, diffused through the rock of the mantle and the crust. A piece of granite might contain only a few parts per million of uranium. If you held it in your hand, you wouldn't feel any heat. The energy released by a single atom decaying is minuscule. But the Earth is massive. The volume of the mantle is 84% of the Earth's total volume. That is billions upon billions of cubic kilometers of rock. When you sum up the tiny heat releases of trillions of atoms decaying across that vast volume, the result is tremendous. Scientific consensus holds that radiogenic heat accounts for roughly the other half of the Earth's heat budget. Think about that for a moment. A significant portion of the energy that moves the continents, half of the energy that creates volcanoes, half of the energy that stops the Earth from freezing solid comes from the spontaneous decay of atoms. It is a silent fire. There are no flames, no smoke, just rocks sitting in the dark, slowly getting warm over millions of years. Potassium-40 is particularly interesting because it is lighter than uranium or thorium. It tends to float upward with the lighter rocks, so the Earth's crust, the layer we live on, is actually enriched with it. The granite continental plates are surprisingly radioactive compared to the deep mantle. In a way, the ground you walk on is a low-grade heating blanket. This radiogenic heating is what confused Lord Kelvin. He assumed the Earth was just cooling down. He didn't realize it was also heating itself up. This process has been going on for 4.5 billion years, but it is slowing down. The half-life of these elements means that over time there is less of them left to decay. 4 billion years ago, the Earth was much more radioactive than it is today. The internal fire was hotter, the tectonic plates moved faster, the volcanoes were more violent. We are living in a calmer, cooler era of Earth's history. The battery is slowly running down. Potassium-40 has a half-life of about 1.25 billion years. A lot of it is gone. Uranium-238 has a half-life of 4.5 billion years, so about half of the original uranium Earth started with has decayed. This slow decay poses an interesting question for our thought experiment about harvesting core energy. If we tapped into this heat, we would be tapping into a nuclear process, but one that is naturally shielded by thousands of miles of rock. It is the ultimate clean nuclear energy. The waste products remain buried in the mantle. Only the heat reaches us. But there is a mystery here, too. Scientists are still debating the exact ratio of primordial to radiogenic heat. To measure it, they have built massive detectors, not to catch heat, but to catch geoneutrinos. These are ghostly particles emitted during radioactive decay. By counting the geoneutrinos coming from the Earth, physicists can estimate how much uranium and thorium is decaying deep down. The results so far confirm that the Earth is indeed a nuclear engine, though the precise balance is still a matter of active research. There is also the question of the core itself. The core is mostly iron and nickel. Uranium and thorium are lithophiles, meaning they love rock. Chemically, they prefer to bind with silicates in the mantle, rather than sinking into the metal core. So, the prevailing wisdom is that the core itself does not produce much radiogenic heat. The nuclear fire is burning in the mantle, wrapping the core in a hot blanket. The core's heat is mostly that ancient primordial stored heat. This distinction is crucial. It means the core is cooling faster than the mantle. The mantle has a heater, the core does not. This temperature difference between the cooling core and the radiogenic mantle drives one of the most important processes on Earth. Convection. Hot rock rises, cold rock sinks. It is a slow, churning motion, like a thick soup simmering on a stove. This movement is what drags the tectonic plates across the surface. It is the reason South America and Africa drifted apart. It is the reason California is slowly sliding past the rest of North America. If we were to bore a hole deep enough to tap this energy, we would be inserting a needle into a living, moving organism. We wouldn't just be finding hot rock, we would be finding rock that flows. We would be encountering the slow-motion currents of geology. This silent decay is the reason the Earth is not Mars. Mars is smaller, so it lost its primordial heat faster, and it likely has less radioactive fuel to keep it warm. Mars died geologically billions of years ago. Its volcanoes stopped. Its magnetic field collapsed. Its atmosphere drifted away. The Earth's size and its radioactive inventory is what keeps it alive. It keeps the rock soft enough to move. It keeps the cycle of carbon going, recycling the atmosphere. So, when we ask, what if the core is an energy source, we are really asking if we can plug into the life support system of the planet. We are looking at a machine that runs on the decay of stars. The uranium in the Earth was created in a supernova explosion billions of years before the Earth existed. We are warmed by the ashes of dead stars trapped inside the rock beneath us. But this heat does more than just move continents. It does something magical in the outer core. It creates a shield. Without this heat, the Earth would be stripped naked by the solar wind. To understand why, we have to look at the relationship between heat, metal, and magnetism. We have to look at the geodynamo. As we descend deeper into the narrative of the Earth, we reach a layer that is crucial not just for energy, but for the very existence of life itself. We have talked about the heat, the primordial fire, and the radioactive decay. But heat alone is just energy. To turn that energy into a planetary shield, you need movement. You need a machine. And deep beneath the rocky mantle, roughly 3,000 kilometers down, lies the most important machine in the solar system, the geodynamo. To visualize where we are, imagine peeling away the Earth's layers. We have passed the thin crust. We have passed the vast, solid but flowing rock of the mantle. Now, we hit a boundary that is as distinct as the surface of the ocean. Below this line, the rock stops. We enter the outer core. This is a sea of liquid iron and nickel, roughly 2,200 kilometers thick. It is a terrifyingly hot ocean, with temperatures ranging from 4,000 to 5,000 degrees Celsius. The pressure here is immense, but the heat is so intense that it overcomes the pressure, keeping the metal in a liquid state. This fluid metal is not sitting still. It is churning. Driven by the intense heat coming from the solid inner core below it, the liquid iron rises. As it reaches the top of the outer core, it cools slightly against the mantle, becomes denser, and sinks back down. This is convection, the same process that makes water boil in a pot. But this is a pot the size of a planet, filled with electrically conductive metal. If the Earth were standing still, this rising and sinking would be simple. But the Earth is spinning. The planet rotates once every 24 hours. This rotation imparts a twist to the moving iron, a force known as the Coriolis effect. The rising columns of molten iron are twisted into spirals, like corkscrews of liquid metal. Now, here is the magic of physics. When you move an electrical conductor, like liquid iron, through a magnetic field, you generate an electric current. And when you generate an electric current, you create a magnetic field. It is a self-sustaining loop. The existing magnetic field induces currents in the moving iron, and those currents reinforce the magnetic field. This is the dynamo effect. It is a massive, natural generator, turning the thermal energy of the core and the mechanical energy of the Earth's rotation into magnetic energy. This invisible force field reaches out from the core, punches through the mantle and crust, and extends thousands of kilometers into space. This is the magnetosphere. And without it, our story would have ended billions of years ago. The sun is not a gentle neighbor. It constantly bombards us with the solar wind. A stream of charged particles, protons and electrons, moving at hundreds of kilometers per second. If these particles struck our atmosphere directly, they would strip away the ozone layer. They would break apart water molecules. Over time, they would erode the atmosphere entirely, leaving the planet dry and dead. This is exactly what happened to Mars. Mars is smaller. Its core cooled down and solidified. The dynamo stopped. The magnetic shield failed. And slowly, the solar wind stripped Mars of its air and water, turning a once blue world into a red desert. Earth's core energy is the only thing standing between us and that fate. The heat we are talking about harvesting is the fuel for the shield. This raises a profound ethical and scientific question in our thought experiment. If we were to tap into the core's heat to power our civilization, would we be stealing from the dynamo? The geodynamo runs on a delicate balance of heat flow. The core must lose heat to the mantle to keep the convection currents moving. If the mantle gets too hot, the core can't shed its heat, and the convection stops. If the core gets too cold, the iron freezes, and the convection stops. By extracting heat, we might theoretically be helping the core cool, perhaps even speeding up the convection in the short term. But on a geological timescale, we are draining the battery that keeps the shield up. Of course, the scale of human energy consumption is tiny compared to the energy of the core. We are like mosquitoes biting an elephant. It is unlikely we could drain enough heat to stop the dynamo, but the concept forces us to respect the interconnectedness of the planet. The light switch in your home, in this hypothetical future, would be powered by the same force that deflects solar storms. The warmth of your toaster would come from the same source that guides migrating birds and compass needles. We also see the evidence of this restless dynamo in the rock record. The magnetic field is not stable. It wanders. The North Magnetic Pole is currently racing across the Arctic toward Siberia. And every few 100,000 years, the field flips entirely. North becomes south, and south becomes north. These reversals are chaotic events, driven by turbulence in the liquid iron ocean. During a flip, the shield weakens, and more radiation reaches the surface. If we were dependent on the core for energy, would we see fluctuations in our power grid as the magnetic poles wandered? Would the turbulence of the deep earth affect the stability of our civilization? The outer core is a place of violence, swirling metals, crushing pressures, and electromagnetic storms. Yet, to us on the surface, it manifests as protection. It is a silent guardian. It is the reason we can breathe. It is the reason the oceans stay in their basins. When you look at the northern lights, the aurora borealis, you are seeing the ghost of the core's energy. You are seeing the solar wind crashing into the magnetic shield, guided toward the poles and lighting up the sky. That green and purple dance is the visible signature of the engine beneath our feet. So, the core is not just a furnace. It is a shield generator. It transforms thermal energy into magnetic armor. As we consider drilling down to tap this power, we must remember that we are approaching the machinery of our own survival. We are not just mining a resource. We are interacting with the heartbeat of the planet. And, as history shows, before we understood this science, we filled that deep, dark space with monsters and myths. Before we had seismographs to listen to the Earth's heartbeat, and before we had physics to explain the heat, we had stories. Humans have always looked up at the sky with wonder, populating the stars with gods and heroes. But when we looked down, our imagination took a darker turn. The ground was where we buried the dead. It was dark, cold, and mysterious. And yet, from this same ground came fire, volcanoes, hot springs, strange vapors. This contradiction birthed the myths of the underworld, a place of both death and hidden power. Almost every culture in human history has a geography of the deep. For the ancient Greeks, it was Hades, a misty, gloomy realm where shadows wandered. It wasn't necessarily a place of punishment, but a place of absence of sun, absence of life. Yet, even in Greek mythology, the deep earth was a prison for the Titans. The giants who had once ruled the cosmos were buried beneath mountains. The eruptions of Mount Etna were said to be the breath of the giant Typhon, struggling against his subterranean chains. Here, we see the first inkling of the truth. The ancients understood that there was a restless, violent energy trapped beneath the rock. In Hebrew cosmology, there was Sheol, a place of stillness. In Mayan mythology, Xibalba was a complex underworld of rivers and trials, a place that heroes had to navigate. But as history moved toward the Middle Ages and the Renaissance, the image of the underworld shifted. It became hotter. Influenced by religious visions of hell, the center of the earth was reimagined as a literal furnace. One of the most fascinating figures to map this imaginary world was Athanasius Kircher, a 17th century Jesuit scholar often called the Master of 100 Arts. In his massive book, Mundus Subterraneus, The Underground World, Kircher drew elaborate cross-sections of the Earth. He envisioned the planet as a Swiss cheese of caverns and tunnels. At the very center, he placed a massive ball of fire. From this central fire, channels, pyrophyllacia, radiated outward, feeding the volcanoes of the surface. He believed the tides of the ocean were pumped through underground tunnels, heated by the central fire and circulated back. Kircher was wrong about the hollow tunnels, but he was intuitively right about one thing: the interconnectedness of heat. He saw the Earth as a machine, a system where the fire below drove the phenomena above. He was trying to give a scientific structure to the energy he knew must be there. Then came the storytellers. In 1864, Jules Verne published Journey to the Center of the Earth. This novel defined the popular imagination of the deep earth for a century. Verne's heroes descend through a volcano in Iceland, finding vast caverns, underground oceans, prehistoric dinosaurs, and glowing fungi. Verne depicted the temperature as manageable, the pressure as survivable. He gave us a hollow earth, a world within a world. It is a beautiful dream. The idea that we could walk to the center of the planet, that there is space for us down there. But science has been a harsh awakener. The reality of the deep earth is far more hostile than Verne imagined. There are no vast, empty caverns deep in the mantle because the pressure is too great. Rock flows like toothpaste to fill any void. There are no underground oceans of water, though there is water trapped inside the crystal structures of minerals. And there are certainly no dinosaurs. But the myth of the central fire persisted because it spoke to a fundamental truth. We instinctively knew the Earth was alive. In the 19th century, before radioactivity was discovered, the central fire was a subject of intense scientific debate. Was the Earth a cooling star? Was it a solid ball that was just hot from friction? It wasn't until the invention of the seismograph that we truly began to see. Seismology is the art of listening to earthquakes. When an earthquake strikes, It sends waves of energy ringing through the planet like a bell. By measuring how fast these waves travel and where they are blocked, scientists can map the interior. In the early 20th century, these sound waves revealed the truth. They showed us that there was no hollow space. They showed us a solid mantle, a liquid outer core, and a solid inner core. They replaced the map of Hades with the map of density and phase states. They replaced the river Styx with currents of molten iron. Yet, even today, the old myths linger in our language. We speak of hellish heat. We think of the deep as a place of danger, and in a way it is done. The conditions at the core, pressures of 3 million atmospheres, temperatures of 6,000 degrees, are effectively hell for any biological matter. No machine we have ever built could survive there for a second. This transition from myth to science is important for our thought experiment. We have moved from fearing the underworld to mapping it. And now we are moving to the next stage, utilizing it. We are no longer content to let the titans sleep beneath the mountains. We want to steal their fire. But there is a hubris in this. The myths often warned against digging too deep. The dwarves of Moria, in Tolkien's fiction, dug too greedily and too deep, and awoke a demon of shadow and flame. While we don't believe in Balrogs, the metaphor holds. The energy density of the deep earth is immense. The pressures are explosive. Tapping into the core is not just an engineering challenge, it is a confrontation with forces that have been buried for a reason. As we prepared to physically touch this realm, we found that the myths of unyielding barriers were truer than we thought. When humanity finally tried to drill as deep as possible, we didn't find dinosaurs or demons. We found something much harder to deal with. We found the heat wall. In the mid-20th century, humanity looked up. We launched rockets of fire and steel, aiming for the moon and the stars. The space race was a spectacle of altitude. But quietly, obscurely, there was another race happening at the same time. It was the race downward, the race to the mantle. While astronauts were floating in the vacuum of space, geologists were trying to pierce the skin of the Earth to touch the engine room. The goal was the MOHO, the Mohorovičić discontinuity. This is the boundary between the Earth's brittle crust and the denser, hotter mantle beneath. Reaching the mantle was considered the geological equivalent of the Apollo landings. It would bring back a sample of the planet's true interior. The Americans tried first with Project Moholy in the 1960s. They decided to drill in the ocean off the coast of Mexico because the crust is thinner under the sea. They managed to drill a few hundred meters into the oceanic floor, proving that deep-sea drilling was possible, but costs and politics killed the project before they ever got near the mantle. Then, the Soviet Union took up the challenge. In the remote, frozen expanse of the Kola Peninsula, near the border with Norway, they began to drill. They weren't looking for oil. They weren't looking for gas. They were drilling purely for science, to see how deep they could go. This was the Kola Superdeep Borehole. Work began in 1970. For nearly 20 years, the Soviets ground their way down, meter by agonizing meter. It was a battle of attrition. The drill string, the steel pipe connecting the rig to the drill bit at the bottom, became kilometers long. Imagine trying to drill a tiny hole in the sidewalk using a strand of spaghetti from the top of the Empire State Building. That is the scale of the mechanical difficulty. The pipe twists, it stretches, it vibrates. But they kept going. They passed 7 kilometers, then 9, then 12. They found microscopic fossils of plankton 2 billion years old. They found water deep in the rock where no one expected it, squeezed out of the crystal structure of minerals by immense pressure. But then, at around 12,262 meters, about 7.6 miles deep, they hit a wall. Not a wall of stone, but a wall of heat. The geologists had predicted that the temperature at that depth would be around 100 degrees Celsius. They were wrong. The temperature soared to 180 degrees Celsius. This might not sound hot compared to the core, but for a mechanical drill, it was devastating. At those temperatures, the rock began to behave strangely. It wasn't brittle anymore. It became plastic. The drillers described it as trying to drill into soup, or plasticine. Every time they pulled the drill bit up to change it, the hole would start to close in on itself, the rock flowing under the immense pressure. The equipment began to fail. The sensors melted. The physics of drilling relied on the rock chipping away, but the rock was refusing to chip. It was bending. In 1992, the drilling stopped. The project was abandoned. The deepest hole humanity has ever dug is just a pinprick. The Earth's radius is 6,371 kilometers. The Kola Borehole reached 12 kilometers. That is 0.2% of the way to the center. If the Earth were an apple, we didn't even break the skin. We just scratched the wax. There is a famous urban legend associated with this hole. You may have heard it. The well to hell. The story goes that the drillers broke through into a hollow cavity and lowered a microphone, hearing the screams of the damned. It was a hoax propagated by a religious newsletter and embellished by tabloids. But the fact that the story went viral speaks to our primal fear of the deep. We want the deep earth to be supernatural because the reality is simply too difficult to comprehend. The reality is that the rock itself becomes an enemy. The failure of the Kola Superdeep Borehole taught us a valuable lesson for our thought experiment. We cannot simply drill our way to the core with brute force. Steel and diamond bits are not enough. The Earth fights back with heat and pressure. If we want to tap the core's energy, we need a fundamentally different approach. We can't just grind the rock. We might have to melt it, vaporize it, or find places where the Earth has already opened a door for us. And nature has opened doors. While the Soviets were struggling with solid rock in the Arctic, other engineers were looking at places where the mantle punches through the crust. Places like Iceland, New Zealand, and the Rift Valley of Africa. Here, the heat is not 12 kilometers down. It is right on the surface. This led to a shift in strategy. Instead of drilling for depth, the prestige of the deepest hole, scientists started drilling for energy density. They stopped trying to reach the moho and started trying to reach the magma. This brings us to the modern frontier of geothermal energy, where we are flirting with forces that are dangerous, unpredictable, and potentially revolutionary. We are moving from the age of hot water to the age of supercritical fluids. In the world of energy, temperature is everything. Traditional geothermal power plants, the kind we have used for decades, are relatively simple. You drill a well into hot rock, pump water down, and it comes back up as steam. That steam spins a turbine. It's a giant underground tea kettle. It's clean, it's reliable, but it's limited. You need specific geological conditions, and the energy output is modest compared to a coal or nuclear plant. But what if you could supercharge that process? What if, instead of gentle steam, you could access water that was so hot and under so much pressure that it stopped acting like water altogether? This is the concept of supercritical geothermal. And the laboratory for this bold experiment is Iceland. Iceland sits directly atop the Mid-Atlantic Ridge, the seam where the North American and Eurasian tectonic plates are pulling apart. It is a land where the mantle is rising. The heat is close. In 2009, a project called the Iceland Deep Drilling Project, IDDP, was drilling at a volcano called Krafla. Their goal was to drill deep, to about 4 kilometers, to find water at extremely high pressures. But at just over 2 kilometers, the drill bit suddenly stopped. It didn't jam. It didn't break. It fell into something soft. They had accidentally drilled directly into a magma chamber. Molten rhyolite at 900 degrees Celsius surged up the borehole. In most drilling operations, this is a catastrophe. It's a volcanic eruption in a pipe. But the Icelandic engineers didn't panic. They capped the well and decided to see what they could do with it. They had created the world's first magma-enhanced geothermal system. They pumped water down toward the magma. The water didn't just boil. Under that immense pressure, over 200 atmospheres and heat, it went supercritical. Supercritical fluid is a state of matter that is like a ghost between liquid and gas. It is as dense as a liquid, so it can carry a huge amount of energy, but it flows like a gas, moving effortlessly through cracks in the rock. When this supercritical water came back up the pipe, it was a monster. It was 450 degrees Celsius. The energy density was 10 times higher than a standard geothermal well. A normal geothermal well generates about 5 megawatts of electricity, enough for a few thousand homes. This single well at Krafla, tapping into the supercritical zone near the magma, was capable of generating 36 megawatts. It was a glimpse of the future. It proved that if we can get close to the heat of the core, or at least the heat of the magma that comes from the core, we can generate massive amounts of power from a tiny footprint. This is the bridge between our current reality and the science fiction idea of core energy. We don't need to drill all the way to the center of the Earth. We just need to drill deep enough to find rock that is 400 or 500 degrees Celsius. At those temperatures, water becomes a superpower fuel. But the risks are real. The Krafla well eventually had to be closed because the valves broke. Supercritical water is highly corrosive. It eats steel. It dissolves minerals like silica and deposits them in the pipes, clogging the system. It is an unruly beast. Taming it requires new materials: titanium alloys, ceramic liners, advanced sensors that can survive the conditions of a furnace. And there is another risk: earthquakes. When you pump high-pressure water deep into the ground, into stressed fault lines, you lubricate the rock. You can trigger slips. In 2006, a geothermal project in Basel Switzerland triggered a magnitude 3.4 earthquake that damaged buildings and terrified the city. The project was shut down immediately. The Earth is under tension. When we stick needles into it, sometimes it flinches. Despite these dangers, the race is on. Japan is looking into this technology. Italy, New Zealand, and the United States are exploring the supercritical frontier. They are developing drills that don't just grind rock but use energy to melt it. They are looking at the crust not as a barrier, but as a boiler lid. This brings us to the edge of what is possible today. We have scratched the surface. We have accidentally poked a magma chamber. We have tasted the power of supercritical fluids. But to truly power a civilization, to replace fossil fuels entirely with the Earth's heat, we need to go deeper. We need to go past the magma chambers into the hard, hot, crystalline basement of the continents. We need to reach depths of 10, 15, maybe 20 kilometers. To do that, mechanical drills are useless. We need something out of science fiction. We need energy beams. We need to vaporize the path ahead. This is where the gyrotrons come in. We have reached a barrier. We have seen how mechanical drills, the spinning bits of steel and diamond that have served humanity for a century, fail when faced with the crushing heat of the deep earth. The Kola Superdeep Borehole taught us that rock becomes soft, jamming the machinery. The depths of 10, 15, or 20 kilometers seemed forever out of reach, locked away by the laws of material physics. But human ingenuity is stubborn. When we cannot push through a wall, we try to burn through it. In the laboratories of fusion energy research, scientists have spent decades developing devices to heat plasma to millions of degrees. They use powerful beams of electromagnetic radiation, generated by machines called gyrotrons. A gyrotron is essentially a high-powered vacuum tube, a cousin of the magnetron in your microwave oven, but vastly more potent. It generates millimeter waves, energy that sits on the spectrum between microwaves and infrared light. For years, this technology was aimed at the stars, or rather at creating stars in jars, fusion reactors like ITER. But recently, a radical idea emerged from the halls of MIT. What if we turned the gyrotron down? What if, instead of heating plasma, we pointed that beam of pure energy at the ground? This is the birth of millimeter wave drilling, and it changes the equation of the deep earth entirely. Imagine a drilling rig that has no mechanical drill bit. There is no spinning metal at the bottom of the hole. There is no friction. There is no jamming. Instead, a beam of intense electromagnetic energy is guided down a smooth pipe. When this beam hits the rock at the bottom, it doesn't chip it away. It vaporizes it. The rock is heated instantly to thousands of degrees. It turns into a cloud of ash and vapor. But here is the elegant part. The intense heat also melts the walls of the hole as it descends. As the beam moves down, the molten rock on the sides cools and hardens into a lining of obsidian, a glass-like, incredibly strong seal. The drill creates its own casing. It effectively turns the earth into a glass pipe, sealing off aquifers, preventing collapses, and isolating the heat. This technology, currently being pioneered by companies like Quaise Energy, promises to breach the heat wall that stopped the Soviets. Because the energy beam has no moving parts, It doesn't care if the rock is 500 degrees or 1,000 degrees. It simply burns through. This opens up a staggering possibility, reaching depths of 20 kilometers. At 20 kilometers deep, the temperature is almost universally high, regardless of where you are on the planet. You don't need to be in Iceland or on a volcano. You could be in the middle of an old, cold continent, beneath a city like London or New York. If you can go deep enough, the heat is there. This is the promise of deep geothermal everywhere. It suggests a future where every city sits on top of its own power plant, drawing terawatts of clean, baseload energy from the basement of the world. But let's pause and visualize what this means. We are talking about piercing the skin of the planet with needles of directed energy. We are talking about vitrifying the crust, turning the chaotic geology of the deep into a structured, engineered conduit. It is a violent process applied for a peaceful purpose. The rock at those depths is under pressure that we can barely comprehend. Thousands of atmospheres. When we vaporize rock in that environment, we are creating a localized, controlled explosion that moves downward. The engineering challenges are still immense. How do you keep the waveguide, the pipe carrying the beam, straight over 20 kilometers? How do you remove the vaporized rock ash from such depths without it clogging the system? And what happens if the beam hits a pocket of pressurized gas? These are the questions keeping engineers awake at night. Yet, the potential reward is a civilization unshackled from surface resources. No more coal mines scarring the landscape. No more vast fields of solar panels competing with farmland. Just a series of small, unobtrusive buildings, humming with the power of the deep. It is a vision of energy independence that is almost absolute. However, as we push deeper with these energy beams, we are entering territory that has been untouched for billions of years. We are not just drilling into rock, we are drilling into time. The rocks at 20 kilometers depth in the continental crust are often the cratonic roots, the ancient, stable cores of continents that have survived since the Archean eon. They have been silent witnesses to the entire history of life on Earth. Vaporizing them is, in a sense, erasing a geological archive. And there is a seismic question. The crust is not a solid block. It is a stack of stressed plates. It is riddled with faults, cracks, and tensions. When we drill deep, even with energy beams, we are altering the stress field. We are creating a void where there was none. We are introducing temperature differentials. Could a network of deep boreholes trigger earthquakes? Could we inadvertently lubricate a dormant fault? The proponents of this technology argue that because the holes are small and sealed with glass, the risk is minimal compared to hydraulic fracturing, fracking, which shatters the rock. But the Earth is a complex, non-linear system. It often reacts in ways our models fail to predict. As we imagine this future, we must also consider the sound. Mechanical drilling is loud, a grinding roar that shakes the ground. Energy beam drilling might be silent on the surface, but deep down, it would be a hiss of vaporization, a continuous thunder of rock turning to gas. It is a new sound for the planet, the sound of humanity burning a path to the mantle. This technology gives us the key to the door. It allows us to step past the 12-kilometer limit of the 20th century. But once we have the key and we open that door, what exactly are we walking into? The mantle is not just hot rock. As we go even deeper toward the core itself, the physics of the planet becomes stranger than fiction. We leave the realm of rock and enter the realm of the crystal heart. We must now turn our minds to the inner sanctum. Let us cast our imagination far beyond the reach of any drill, past the mantle, past the churning liquid ocean of the outer core. We are going to the very center, the inner core. This is a place that was only discovered in 1936 by a Danish seismologist named Inge Lehmann. Before her, scientists thought the Earth's core was entirely liquid. But Lehmann noticed something subtle in the seismic waves traveling through the planet. Some waves were bouncing off something hard in the center. They were speeding up. She realized there was a solid sphere inside the liquid. The existence of the inner core is a paradox of physics. The temperature here is estimated to be around 6,000 degrees Celsius, hotter than the surface of the sun. At such temperatures, iron should be a gas, let alone a liquid. But the pressure changes everything. The weight of the entire planet bears down on this point. The pressure is over 3.6 million atmospheres. Under this crushing hug of gravity, the iron atoms are forced together so tightly that they cannot melt. They are locked into a crystal lattice. The inner core is a solid ball of iron-nickel alloy, roughly the size of the moon, growing slowly in the darkness. It is the most alien object in the solar system, and it is right beneath us. But this is not just a lump of cold iron. It is a dynamic, growing crystal. As the Earth slowly cools, the liquid iron at the bottom of the outer core freezes onto the surface of the inner core. This freezing process releases heat. Latent heat of crystallization. This is a critical addition to our energy inventory. The growing inner core is a heater. It is actively powering the dynamo above it. It has been growing for perhaps 1 billion years, a slow accumulation of frozen metal. Seismologists have found that the inner core is not uniform. Seismic waves travel faster through it when they move from north to south, pole to pole, than when they move through the equator. This phenomenon, called anisotropy, suggests that the iron crystals are aligned. They have a grain, like wood. Imagine a crystal the size of the moon, with all its atoms lined up in the same direction. What force aligns them? Is it the magnetic field? Is it the rotation? There is also the mystery of superrotation. Some studies suggest that the inner core spins slightly faster than the rest of the planet. It is unmoored, floating in the liquid outer core, and the magnetic torque might be spinning it up. Imagine the Earth's heart racing ahead of its body. This differential rotation could be a source of friction, another hidden battery of energy. Recent theories have added even more texture to this picture. Some scientists propose that iron snow falls from the outer core onto the inner core. Flakes of solid iron forming in the liquid and drifting down to settle in piles on the solid surface. Imagine a landscape of iron dunes, buried under miles of liquid metal, constantly shifting. Others suggest the inner core is soft, that despite being solid, it might have the consistency of gold or lead near its melting point, able to deform and wobble. Why does this matter for our energy thought experiment? Because the inner core is the ultimate stabilizer. It is the flywheel of the Earth. Its growth drives the convection that powers the magnetic shield. If we were to drain the heat from the system too fast, we might affect the rate at which the inner core grows. If we stop the growth of the inner core, we stop the release of latent heat. We starve the geodynamo. We turn off the shield. It is a reminder that the Earth is not a static tank of fuel. It is a process. The inner core is a freezing process that has been running for 1 billion years. It is a delicate phase transition between liquid and solid that dictates the magnetic future of our world. Furthermore, there is a hypothesis that the center of the Earth contains a natural nuclear reactor, a georeactor. While most scientists believe the uranium sank to the core mantle boundary or stayed in the mantle, some maverick physicists have proposed that a ball of uranium could have collected at the very center of the inner core. If this were true, and it is highly speculative, the Earth would literally have a fission reactor at its heart. This would explain some of the excess heat and helium isotopes we see. If the core is a nuclear reactor, then our battery is actually an engine that runs on fuel, and fuel can run out. The inner sanctum is a place where intuition fails. Matter here behaves in ways we can only simulate in supercomputers. Iron becomes a hexagonal crystal. Elements like light hydrogen or oxygen might be trapped between the iron atoms, changing the chemistry. It is a realm of extreme order, the crystal, surrounded by extreme chaos, the liquid. We will likely never touch the inner core. Even with energy beams, the pressure is insurmountable. But understanding it is crucial. It reminds us that the energy we hope to harvest at the surface is the echo of a profound transformation happening 6,000 kilometers down. The heat in your radiator, in this geothermal future, would be the heat of a planet freezing itself solid from the inside out. But as we ascend from the core, back through the mantle and into the cooler crust, we encounter another surprise. We used to think that life was a surface phenomenon, clinging to the sunlight. We were wrong. The deep Earth is not dead. It is teeming. For centuries, biology was the study of the sun's children. Plants ate sunlight. Animals ate plants. We ate both. The food chain began with a photon traveling from the sun to a leaf. We assumed that where the sun didn't shine, life couldn't exist. We assumed that the deep rocks were sterile, too hot, too tight, and too starved of energy to support anything more than perhaps a stray dormant spore. But in the last few decades, we have opened the Earth and found it staring back at us. We have discovered the deep biosphere, sometimes called the dark biosphere. It turns out that life does not need the sun. It only needs energy. And the Earth provides plenty of it. Deep in gold mines in South Africa, nearly 4 kilometers underground, scientists found something impossible. In water that had been trapped in the rock for thousands of years, isolated from the surface, they found worms. Not microscopic bacteria, but complex multicellular nematodes. They named one species Halocephalobus mephisto, the devil worm, after Mephistopheles, the demon of the underworld. This worm doesn't know the sun exists. It feeds on biofilms of bacteria. And what do the bacteria eat? They don't eat sunlight. They eat the rock itself. They are chemolithotrophs, rock eaters. They feed on hydrogen gas that is released when water reacts with radioactive minerals in the crust. Think about the implications of this. The radiation from the uranium we discussed earlier, the silent decay, splits water molecules, radiolysis, creating hydrogen. The bacteria eat the hydrogen. The worms eat the bacteria. This is a completely independent ecosystem. It is a food chain that runs on nuclear energy, not solar energy. It is an alien world right here on Earth, and it is not small. When scientists estimate the total amount of life in the deep Earth, the microbes living in the pores of sandstone, in the cracks of granite, in the sediments of the ocean floor, the numbers are staggering. Some estimates suggest that the biomass of the deep Earth, the sheer weight of all that carbon, rivals the biomass of all marine life in the oceans. There might be more life inside the Earth than on top of it. These organisms live in zombie states. Because resources are scarce and space is tight, they metabolize incredibly slowly. Some microbes in the deep ocean sediments might divide only once every 100 or even 1,000 years. They are playing the long game, surviving on the faintest trickles of chemical energy. They are masters of efficiency. Now, bring this back to our energy thought experiment. If we start drilling thousands of boreholes 20 kilometers deep, we are not drilling into sterile rock. We are drilling into a living biome. We are piercing a hidden ecosystem that has been isolated for eons. This raises practical and ethical problems. First, biofouling. If we create a geothermal reservoir, giving these deep microbes a sudden influx of space and water, will they bloom? Will they clog our pipes and eat our equipment? The deep Earth is full of sulfate-reducing bacteria that produce hydrogen sulfide, a corrosive, toxic gas. We might drill a well for clean energy and end up uncorking a biological weapon of sour gas, produced by trillions of newly awakened microbes. Second, there is the risk of contamination. If we pump surface water down, we are introducing surface bacteria to the deep. This is an invasion. We could wipe out ancient ecosystems before we even understand them. We might be destroying the most unique biological library on the planet. Organisms that could teach us about the origins of life, or how to survive on Mars. Because if life can exist 5 kilometers deep in the Earth's crust, feeding on radiation and rock, then why not on Mars? Why not on Europa? The deep biosphere is our best analog for extraterrestrial life. By exploiting the core's heat, we are effectively industrializing the only alien-like habitat we have access to. There is also a wilder theory. The deep, hot biosphere model, proposed by astrophysicist Thomas Gold. He suggested that life didn't start on the surface and migrate down. He argued it started in the deep and migrated up. He believed that the deep Earth is the true cradle of life, a protected incubator safe from the asteroid impacts and radiation that sterilized the early surface. If this is true, then by drilling deep, we are returning to our ancestral home. The energy of the core is not just thermal, it is chemical. It drives the reactions that feed this dark kingdom. As we envision a future powered by the Earth, we must acknowledge that we are not the only ones using this battery. The devil worms and the rock-eating bacteria were here first. They have been running on geothermal power for billions of years. We are just the new tenants trying to tap into the line. This realization adds a layer of complexity to the clean energy narrative. Is energy truly clean if it disrupts a hidden biosphere? Is it renewable if it relies on a delicate geochemical balance that life depends on? The Earth is not just a rock. It is a sponge soaked in life. And as we suck the heat out, we are changing the temperature of their universe. But what happens if we succeed? What happens if we drill the holes, manage the biology, and start drawing terawatts of power from the mantle? We solve our climate crisis. We stop burning carbon. But thermodynamics is a strict accountant. You cannot take energy without a cost. If we drain the heat, the planet must cool. And a cooling planet faces a different kind of death. Thermodynamics is the law that rules the universe, and its second law is particularly unforgiving. Entropy increases, and energy flows from hot to cold until equilibrium is reached. The Earth is trying to cool down. It wants to be in equilibrium with the cold vacuum of space. Our atmosphere, our crust, and our internal heat generation are just slowing down this inevitable march toward the big chill. Currently, the Earth cools naturally. The 47 terawatts of heat flowing out is the planet shedding its energy. This is secular cooling. It is a slow process, claiming perhaps 50 to 100 degrees Celsius of internal temperature every billion years. It is a pace that allows geology to adapt. The plates slow down gradually. The magnetic field adjusts. Life evolves. But what if humanity becomes a significant geological force? What if we plug 1 billion cables into the mantle and start drawing power? If we replaced all fossil fuels, nuclear, solar, and wind with geothermal energy, we would be extracting roughly 20 terawatts of power today. But our energy needs are growing exponentially. In a few centuries, we might need 100 terawatts, then 500. At some point, we stop being passive observers of the cooling and become active agents of it. We become a heat sink. We would be accelerating the death of the planet to fuel our civilization. This is a classic tragedy of the commons, but on a planetary scale. The core's heat seems infinite, just as the fish in the sea seemed infinite, just as the buffalo on the plains seemed infinite. But it is not. It is a finite inventory of joules. If we extract heat faster than radiogenic decay can replenish it, and we likely would, as the decay is slow, we are actively refrigerating the Earth. What are the consequences of a cooler Earth? Look to Mars. Mars is a cautionary tale written in red dust. Because it cooled faster, its outer core solidified. When the liquid iron stopped moving, the dynamo stopped. The magnetic shield vanished. The solar wind stripped the atmosphere. The water evaporated into space. The planet died. If we cool the Earth's core, we risk the same fate. It wouldn't happen in a human lifetime, or even in the lifetime of a civilization as we know it. It would take millions of years to significantly drain the battery. But the ethical question remains: do we have the right to shorten the lifespan of our planet? Are we willing to trade 1 billion years of future habitability for a few thousand years of unlimited energy now? A cooler mantle means more sluggish tectonics. The continents would stop drifting. Mountains would stop rising. Erosion would eventually wear the land flat, and without tectonic uplift to build it back, the world would become a water world, or a stagnant desert. The carbon cycle, which relies on volcanoes to recycle carbon from rocks into the atmosphere, would break. The thermostat of the planet would fail. And then there is the magnetic field. As we discussed, the dynamo runs on the heat difference between the core and the mantle. If we extract heat from the mantle, we might actually increase the temperature difference initially, making the dynamo run harder. But eventually, as the overall system loses energy, the convection would falter. A flickering magnetic field would let in bursts of cosmic radiation. Our satellites would fry. Our power grids would collapse. Cancer rates would soar. Evolution would be driven by radiation mutation. We are playing with the master controls of the spaceship. We are thinking about the Earth as a resource, like a coal mine, rather than as a closed system. However, proponents of geothermal energy argue the math is on our side. The total heat content of the Earth is roughly 10 to the 31st joules. Human consumption is minuscule compared to this. We could power our current civilization for billions of years and barely drop the temperature by a degree. They argue that the sun will append and swallow the Earth long before we could ever drain the core. They say the battery is so big that for all practical purposes, it is infinite. But human ambition is not static. We are an exponential species. If we have unlimited energy, we will build more, travel further, compute more. We might build planetary-scale computers, terraform other worlds, or launch armadas of starships. Our hunger for energy has no known limit. Given enough time and enough exponential growth, even the Earth's core becomes a small battery. There is a melancholy beauty in this realization. We are huddled around the fire of our planet, warming our hands. We know the fire will eventually go out. The stars will burn out. The universe itself will cool. By using geothermal energy, we are accepting our place in this thermodynamic flow. We are using the dying breath of the Earth to fuel our dreams. Perhaps the ultimate destiny of Earth is to be consumed by its children. Maybe a planet is meant to be a battery that jumpstarts a civilization, allowing it to eventually leave the nest and find new energy among the stars. In this view, draining the core is not a crime. It is a hatching. We use the egg to grow, and then we break the shell. But until we leave, we are tethered to this cooling rock. We must balance our hunger with the health of the engine. We must understand that the ground beneath us is not dead matter. It is a dying star, trapped in rock, giving us its final warmth. And, as we stand on the precipice of this new energy age, we must ask ourselves, what kind of society would we build with this power? If energy was limitless, coming from beneath every city, how would that change us? Let us indulge in a moment of pure imagination. Let us step away from the technical limitations of drills and beams for a moment and step into a future where the problem is solved. Imagine a world where the heat wall has been breached, where the deep earth is as accessible to us as the open sky. What does a civilization look like when it is powered not by the burning of ancient forests, fossil fuels, or the capture of fleeting photons, solar, but by the steady, eternal pulse of the planet's core? This would be the rise of a civilization of the depths. The first and most profound change would be the geography of power. Throughout human history, civilization has been dictated by resources found on the surface. We built cities near rivers for water mills. We fought wars over coal seams in the 19th century and oil fields in the 20th. We are currently scrambling for lithium deposits and sunny deserts. Our geopolitical map is a map of unevenly distributed luck. Some nations have oil, others do not. Some have sun, others have winter. But the heat of the core is the great equalizer. At 20 kilometers down, the Earth is hot everywhere. It does not matter if you are in Saudi Arabia or Siberia, in the Amazon or Antarctica. Beneath the feet of every nation lies the same 500-degree rock. In this future, energy independence is absolute. Every city, every town, perhaps even every large building, sits atop its own power plant. The massive transmission lines that currently scar our landscapes, carrying electricity from distant dams or solar farms to the cities, would vanish. The grid would become decentralized, a cellular network of self-sufficient nodes. This shift would reshape our architecture and our habitation. If energy is limitless and ubiquitous, we can live anywhere. We could build thriving metropolises in the frozen wastes of the Arctic, heated by the ground beneath them, glowing like warm jewels in the polar night. We could construct underground cities, not as bunkers, but as garden worlds, using the Earth's energy to power artificial suns, growing food in vertical farms buried deep in the bedrock, protected from the storms and climate chaos of the surface. Our relationship with time would change. Solar and wind are cyclical. They bind us to the rhythm of day and night, summer and winter. We need batteries to bridge the gaps. But core energy is base load. It is constant. It does not sleep. It does not wane. A civilization powered by the core operates on a flat line of continuous output. This stability might allow for projects of immense scale. Desalination of oceans, carbon capture from the atmosphere, processes that are currently too energy-intensive to be practical. We could clean the surface using the power of the deep. Culturally, we might see a shift in our mythology. For centuries, we have worshipped the sky, sun gods, sky fathers. We look up for salvation. But in this future, we might turn our gratitude downward. We might develop a geocentric spirituality, revering the ground as the mother, the provider. The central fire of the ancients would return, not as a hell, but as a hearth. We would be a species huddled around the planetary campfire, understanding that our warmth comes from the rock. However, this abundance brings its own dangers. Energy is the currency of action. With unlimited energy, we can reshape the physical world. We could level mountains, drain seas, and synthesize materials on a massive scale. If we are not wise, a civilization of the depths could become a civilization of destruction, using the Earth's own power to scar its surface even faster. We might become a heat-flush society, radiating so much waste heat from our machines and cities that we alter the local climate, creating urban heat islands that rival volcanoes. There is also the paradox of the commons regarding the subsurface. Who owns the heat 20 kilometers down? If I drill a hole in my backyard and extract heat, and my neighbor does the same, do we cool the rock between us? Do we steal each other's thermal pressure? International law currently governs the surface and the sea, but the deep crust is a legal Wild West. We can imagine future conflicts not over land, but over thermal rights. Subterranean wars fought with directional drilling and heat-sapping technology. And what of the psychological shift? To live by the core is to acknowledge our precarious position. We would be constantly aware that we are tapping into a finite, cooling object. It might instill a sense of planetary mortality. We might become more protective of the Earth, realizing that every jewel we take is a jewel that will never return. Or we might become fatalistic, deciding to burn the candle at both ends, using the Earth up to launch ourselves into the cosmos. Imagine looking out your window in this future. The air is clear because there is no smog, no exhaust. The skyline is quiet. There are no smokestacks. But if you look at the thermal imaging sensors, you see the ground glowing. Beneath the parks and the streets, deep shafts of glass-lined rock plunge into the darkness, carrying the invisible fire upward. You put your hand on the wall of your home, and it is warm, humming with a vibration that travels all the way from the mantle. This civilization would be more grounded, literally and metaphorically. We would be miners of heat, farmers of temperature. We would have reconciled the surface with the deep, ending the fear of the underworld and replacing it with utility. But as we settle into this comfortable dream, the Earth itself might have something to say. Because the planet is not a passive battery, it is a stressed, creaking, moving system. And when you poke a stressed system, it tends to snap. We must now turn to the most immediate and terrifying risk of this future: the environmental equation of the Earth's crust. Every action has a reaction. This is Newton's third law, and it applies to geology as much as it does to rockets. We tend to think of the ground as solid and immovable, but seismologists know the truth. The Earth's crust is in a state of critical equilibrium. It is like a loaded spring, or a house of cards, held together by friction and pressure. The tectonic plates are constantly pushing against each other, building up stress over centuries. When that stress overcomes the friction, the rock slips and we get an earthquake. Now, imagine injecting the human variable into this delicate balance. The environmental equation of core energy is not about carbon emissions. It is about mechanical stability. It is about the risk of induced seismicity. We have already seen previews of this movie. In the early 2000s, the city of Basel in Switzerland launched a hot, dry rock geothermal project. They drilled 5 kilometers down and started pumping water under high pressure to fracture the granite and create a heat exchanger. The idea was to create artificial cracks where water could flow, pick up heat, and return to the surface. It worked. But as the water pressure increased, it did something else. It lubricated existing ancient fault lines that no one knew were there. On December 8, 2006, the ground shook. A magnitude 3.4 earthquake struck the city. It wasn't a catastrophe. Chimneys cracked, bells rang, people ran into the streets in their pajamas. But it was a wake-up call. The city government shut the project down immediately. They realized they were playing Russian roulette with the tectonic stresses beneath their feet. More recently, in 2017, the city of Pohang in South Korea was hit by a magnitude 5.4 earthquake. It injured dozens of people and caused millions of dollars in damage. Extensive forensic investigation revealed that an experimental enhanced geothermal system, EGS, plant nearby was the trigger. By injecting fluid into the ground, they had unlocked a fault that had been waiting to slip. These are the risks at 5 kilometers. Now, extrapolate this to our thought experiment of 20 kilometers. At those depths, the lithostatic pressure is immense. The potential energy stored in the rock is vast. If we use energy beams to vaporize rock, we are creating voids. If we circulate fluids, we are changing pore pressures. We are effectively performing acupuncture on a giant that is prone to muscle spasms. The scientific community is divided on the scale of this risk. Some argue that millimeter wave drilling, the glass-lined shafts, would be safer because it doesn't involve fracking or shattering the rock to create flow. It relies on conduction from the hot rock to the pipe. It is a closed loop. If we don't inject fluid into the rock itself, the risk of lubricating faults is lower. But others argue that the sheer act of cooling the rock creates fractures. Thermal contraction. As we extract heat, the rock around the borehole cools and shrinks. This shrinking creates cracks. These cracks could propagate, reaching out into the surrounding stressed rock, potentially triggering a slip. If we have thousands of these boreholes under a major city, are we slowly weakening the foundation of that city? Are we creating a man-made seismic zone? There is also the butterfly effect of geology. The Earth is a non-linear chaotic system. A small change in pressure here could trigger a release of stress 50 miles away. We simply do not have a map of the deep crust detailed enough to know where every fault line lies. We are drilling blind into a spiderweb of tensions. And let's look deeper. If we extract significant heat from the mantle boundary, we change the viscosity of the rock. Cold rock is stiffer, hot rock is softer. By creating cold spots in the mantle, we could alter the flow of convection currents. This is speculative, of course, on human timescales, but over centuries. Could we inadvertently redirect the slow river of rock that drives plate tectonics? Could we stop a volcano in one place only to have it burst forth in another? The environmental cost might also be chemical. We mentioned the deep biosphere. If our boreholes fail, if the glass lining cracks, we could have cross-contamination between deep aquifers. We could bring up brines, salty, mineral-rich radioactive water from the deep, and spill it onto the surface. We could accidentally release pockets of abiotic methane or hydrogen sulfide trapped for eons. The cleanliness of geothermal energy is relative. It is clean for the atmosphere, no CO2, but it is messy for the lithosphere. It trades climate risk for seismic risk. It trades the pollution of the air for the disturbance of the rock. This brings us to a concept called planetary stewardship. If we are to become a civilization that draws its life from the core, we must become better listeners. We cannot just take. We must monitor. We would need a global network of sensors, listening to the groans and creaks of the deep earth in real time. We would need to be able to throttle our energy usage instantly if the stress levels get too high. We would need to treat the earth not as a dead resource, but as a partner in a dance. The environmental equation tells us that there is no such thing as a free lunch in physics. Energy comes from somewhere. Extracting it always leaves a scar. The question is whether we can heal those scars, or if they will accumulate until the ground beneath us decides to shake us off. As we near the end of our journey, we are left with a picture of a planet that is far more dynamic. far more powerful and far more fragile than we usually perceive. We have looked at the fire, the shield, the life, and the risks. Now, it is time to close the circle. It is time to listen to the echo of the core one last time. We have traveled far tonight, without ever leaving the room. We have descended through the floorboards, past the tangled roots and the water tables, through the granite skin of the continents, and into the crushing, flowing, burning dark. We have stood at the edge of the iron catastrophe, watched the birth of the moon, and felt the silent heat of decaying atoms. We have seen the geodynamo spinning its protective web around our world, and we have imagined a future where humanity finally plugs into this planetary engine. Now, I want you to return to the present moment. Feel the weight of your body pressing down. That gravity you feel is the same force that pulled the iron to the center of the earth 4.5 billion years ago. It is the same force that keeps the pressure high enough to keep the engine running. You are connected to the core by the invisible tether of gravity. Listen to the silence around you. It seems empty, but by now, you know it is not. Beneath the silence is a hum. The earth is never truly still. It is vibrating with the microsysms of ocean waves hitting the shorelines, with the tidal pull of the moon, with the thermal expansion of the dawn. And deeper, much deeper, is the hum of the dynamo, the churning of the metal ocean that keeps us safe. The question we asked tonight, what if Earth's core is another energy source, is not really a what if. It is an energy source. It is the original energy source. It is the reason the Earth is habitable. It is the reason the atmosphere clings to the rock. It is the reason the continents rise from the sea, creating land for us to walk on. We have been living off the core's energy since the first single-celled organism emerged in a hydrothermal vent, bathed in the heat of the interior. Whether we ever drill 20 kilometers down, whether we ever build the energy beams or the glass shafts, matters less than the realization of where we are. We are inhabitants of a living world, a world that is hot, dynamic, and finite. We are not standing on a dead stage. We are riding a cooling star through the darkness of space. The story of the core is a story of time. It connects us to the supernova that forged our uranium. It connects us to the collision that formed the moon. And it connects us to the deep future, where the Earth will eventually cool, the dynamo will stop, and the planet will rest. But that rest is billions of years away. For now, the heart is beating. The furnace is burning. There is a comfort in this. We often feel small and disconnected in the modern world. We feel separated from nature by our concrete and our screens. But the geology beneath us is a reminder that we can never truly be separated. The heat that warms your home, ultimately, is part of the same budget that drives the volcano. The magnetic field that guides your phone's GPS is generated by the iron ocean. We are woven into the physics of this sphere. If you enjoyed this descent into the deep, if you found calm in the crushing pressures and the blinding heat, I would be grateful if you gave this video a like and subscribed to Mysteries Beneath Earth. It helps this little channel grow, like a crystal slowly forming in the dark. As you drift towards sleep, imagine that warm, protective glow beneath you. Not a fire of destruction, but a fire of creation. A fire that has burned for eons to keep the cold of space at bay. You are safe. You are held by gravity. You are shielded by magnetism. And you are warmed by the ancient memory of the birth of the world. Good night.